This code imports various necessary libraries such as OS, Pandas, Matplotlib, Seaborn, Warnings, NumPy, and others. It filters out warning messages, sets the p for the Matplotlib plots, and imports specific modules like Gaussian NB from Sklern and SB classifier from SBoost. This code imports various modules and functions from different libraries for a stock prediction project using machine learning. The stats models module is used for time series analysis and modeling, including ARIMA and Seramax models. Functions like plot_pitchf and plot_ikf are used for plotting autocorrelation and partial autocorrelation plots. The Sklern module is used for evaluating the model's performance metrics such as mean squared error, confusion matrix, F1 score, and accuracy score. The pandas.plotting module is used for plotting autocorrelation plots for the data. This code imports various libraries needed for stock prediction using machine learning. It imports the TensorFlow Keras library, the RMSprop optimizer from TensorFlow, the partial function from the functools library, the optimizers module from TensorFlow Keras, the sequential and model classes from TensorFlow Keras models, and different layers from TensorFlow Keras layers. The code also imports the Bayesian optimization class from a library called Bayes_opt, and the plot_model function from TensorFlow Keras utils. Overall, this code sets up the necessary libraries and functions for stock prediction using machine learning and Bayesian optimization. This code imports two modules, functions and plotting. These modules are likely custom modules written for the purpose of stock prediction using machine learning. The functions module likely contains functions that handle various calculations and operations related to stock prediction, such as data preprocessing, feature engineering, model training, and model evaluation. The plotting module likely contains functions to visualize and plot the results of the stock prediction, such as plotting the actual stock prices versus predicted values, visualizing the performance of different models, or plotting various metrics related to the prediction accuracy. By importing these modules, the code can access the functionality provided by these modules and use it for its stock prediction task. This line of code sets the random seed value to 66 for the NumPy library. Setting the random seed ensures that the random numbers generated by the program are reproducible. This is useful when working with machine learning algorithms that involve random elements, as it allows for consistent results to be obtained each time the program is run. This code is for stock prediction using machine learning. It starts by accessing a directory called data/stocks and listing all the files inside it. It then creates an empty dictionary called stocks. Using a loop, the code checks each file in the directory and filters out only the ones with the file extension .csv. For each eligible file, it extracts the name, without the extension, and assigns it to the variable name. Next, it reads the CSV file using pandas read_CSV function and assigns it to the dictionary stocks with the name as the key. The index_col parameter is set to date, indicating that the date column will be used as the index for the data. Finally, the code converts the index column to datetime format using pandas to_datetime function, ensuring that the dates are formatted correctly for further analysis. This code defines a function called baseline_model that takes in a series or array of stock data. The function generates a series of random numbers between 0 and 1, with the same length as the input stock data. These random numbers are then compared with the true values of the stock data using a binary classification approach. The accuracy of these baseline predictions is calculated using the accuracy_score function, and this accuracy score is returned as the output of the function. The code uses the NumPy library for generating random numbers and the functions.binary function to convert the input stock data into a binary format. This code computes the accuracy of a baseline model for stock prediction using machine learning. It passes the returns data of the TSLA stock to the baseline_model function and stores the computed accuracy in the variable baseline_accuracy. The next line prints the accuracy in percentage format. This code snippet starts by initializing an empty list called base_preds. Then, it runs a loop 1000 times and calls a function called baseline_model with the argument stocks_slim. Return for each iteration. The return value of the function call is appended to the base_preds list. After the loop, the code creates a figure with a size of 16 by 6 using matplotlib. It sets the style to Seaborn white grid and creates a histogram using the data in the base_preds list. The histogram has 50 bins and uses the color hashtag 4AC2FB. A title baseline model accuracy is added to the plot with a font size of 15. The code also adds a vertical line at the mean value of the base_preds array, using a black color and a dashed line style. Finally, the plot is displayed. This code prints the number of entries in the historical data of Tesla stocks. It uses the format function to insert the value of the number of entries into the print statement. The next line of code retrieves the first few rows of the return column from the historical data of Tesla stocks and displays them. This code is using the matplotlib library to plot the autocorrelation function, ACF, of the returns of a stock with the ticker symbol TSLA. The ACF measures the correlation between a stock's returns and its past returns at different time lags. The plot is set to have a figure size of 16 by 3. The plot created will display the ACF with lags ranging from 0 to 299. This code is performing stock prediction using machine learning. It first defines a list of orders, which represents different configurations for the ARIMA model. It then selects a subset of stock data for training and testing. The code iterates over each order in the list and tries to fit an ARIMA model to the training data. It then uses the fitted model to make predictions for the test data. The predictions are stored in the order_predictions list. After making predictions for all test data, the code calculates the accuracy of the predictions by comparing them to the actual values using the accuracy_score function. The accuracy is printed to the console. If an order fails to be processed, which could be due to an incorrect configuration, an error message is displayed indicating that the order is wrong. Finally, the code stores all the predictions in the all_predictions dictionary. This code is used to plot a graph displaying the test data and the predicted data for stock prices. It creates a figure with a specific size, then plots the test data and the predictions on the graph. It adds legends, a title, and labels to the graph. It also includes an annotation with an arrow on the graph to indicate a specific point. Additionally, it adds a patch in the form of a rectangle to highlight a specific region on the graph. Lastly, it creates a smaller subplot within the main plot to show a zoomed-in view of the test and predicted data for the first 30 days. The subplot has no axis labels and is titled lag. The graph is then displayed. This code generates a histogram plot comparing the distribution of true stock returns, TSLA, and the predicted stock returns. The data used for the histogram is a subset of the TSLA stock returns from index 1900 to 2300. The true stock returns are plotted in blue, while the predicted stock returns are plotted in pink with some transparency. A vertical dashed line at 0 is also plotted. The title of the plot is RNN true versus predicted values distribution, and a legend is included to differentiate between the true and predicted values. Finally, the plot is displayed. This code is performing stock prediction using machine learning. The first two lines of code create binary variables for the test and train datasets. Then, the confusion matrix is calculated using the test and train variables, and the values for true negatives, dn, false positives, fp, false negatives, fn, and true positives, tp, are retrieved from the confusion matrix. The accuracy score is then calculated using the test and train variables. Finally, the code prints the sum of true positive and negative predictions, the sum of false positive and negative predictions, and the accuracy percentage. This code imports the pandas library and uses it to read a CSV file called Tesla_headlines.csv. The file contains headlines related to the stock market performance of the company Tesla. The index_col parameter is set to date, which means that the date column in the CSV file will be set as the index for the resulting data frame. This code assigns the result of joining the Tesla stock data with the average sentiment for each date from a dataset called Tesla_headlines to the variable Tesla. The purpose of this code is to combine the stock data with the corresponding sentiment data for Tesla, which can be used for stock prediction using machine learning techniques. This code is a part of stock prediction using machine learning. It is specifically related to the Tesla stock. The fillna function is being used on the Tesla variable. Fillna is a function used to replace missing values in a data frame or series. In this case, the missing values are being replaced with the number 0. The in-place equals true parameter ensures that the changes are made directly to the Tesla data frame without creating a new object. This code creates a line plot that compares the sentiment of news about Tesla stock to the daily return of the stock. It uses the Seaborn white grid style and sets the figure size to 16 by 6. The plot shows the sentiment data from the January 10, 2019 to September 5, 2019 shifted by 1 day, represented by the blue line labeled News Sentiment. It also shows the daily return data for the same period, represented by the pink line labeled Return. The plot includes a legend, a title, and is displayed using the plt.show function. This code creates a pandas data frame that computes the correlation between two columns in a dataset. The sentiment column is created by shifting the sentiment column of a dataset called Tesla by 1 index. The return column is created by selecting the return column of the Tesla dataset within a specified date range. The function core is then applied to the data frame to calculate the correlation between these two columns. This code creates a scaled version of the Tesla stock data using a scaling function. The function used is called scale from the functions module. The scale range for the data is specified as 0, 1, meaning that the scaled values will range from 0 to 1. The resulting scaled data is stored in the variable scaled_Tesla. This code first assigns the variable x to a subset of the scaled_Tesla data, discarding the last item in the dataset. It then assigns the variable y to the return column of the Tesla stocks data frame, with a value shift of -1, and drops the last item from the resulting series. This code creates an instance of this classifier class, which is a classifier algorithm used for machine learning. The fit method is then called on this classifier instance, passing in a subset of the input data x and corresponding labels y. This fit method trains the classifier on the provided data, allowing it to learn patterns and make predictions. This code calculates and plots the feature importance of a machine learning model trained for stock prediction. First, it creates a data frame called important_features that contains two columns: feature, which represents the names of the features used in the model, and importance, which represents the importance of each feature in the model as calculated by the XGBoost algorithm. Next, it sorts the rows of the important_features data frame in ascending order based on the importance column. Then, it creates a bar plot using the sorted important_features data frame. The horizontal bars represent the feature names, while the lengths of the bars represent the importance of each feature. The color of the bars is set to #4AC2FB. The title of the plot is set as XGBoost, feature importance, Tesla, with a font size of 15. The x-axis label is set as importance, with a font size of 13. Finally, it displays the plot. This code defines a variable n_steps as 21. It then scales that SLA column from the stock data frame using the scale function. The scaled SLA data is then used to split sequences into training and testing sets. The training set, denoted as x_train and y_train, is created by taking the scaled SLA data, excluding the last element, and the shifted return values from the stock's data frame, excluding the last element, using the split_sequences function. The last argument of split_sequences is set to split equals true and a ratio of 0.8, indicating that the sequences should be split into training and testing sets with a ratio of 80% for training. The testing set, denoted as x_test and y_test, is created similarly, but using the remaining 20% of the data. Overall, this code prepares the data for stock prediction using machine learning by scaling the input data and splitting it into training and testing sets. This code is implementing a stock prediction model using machine learning. The code starts by clearing the keras session. Then, it defines the number of time steps and features in the training data. Next, it creates a sequential model. The model architecture consists of two LSTM, long short-term memory, layers. The first LSTM layer has 100 units and uses the ReLU activation function. It returns sequences of outputs. The input shape is determined by the number of time steps and features. The second LSTM layer has 50 units and also uses the ReLU activation function. It does not return sequences of outputs. After the LSTM layers, there are two dense layers. The first dense layer has 10 units. The second dense layer has 1 unit. The model is compiled using the atom optimizer, mean squared error, (MES), as the loss function, and mean absolute error, (MEA), as the metric. The code snippet model.summary is used to generate a summary of a machine learning model. This summary provides information about the layers in the model, the number of parameters in each layer, and the total number of trainable parameters in the model. It also shows the shape of the input and output tensors for each layer. This summary is useful for understanding the structure and complexity of the model, and it can help in troubleshooting and optimizing the model during the development process. The code is fitting a machine learning model to x_train and y_train data for 100 epochs. It is using the x_test and y_test data for validation during the training process. The use_multiprocessing flag indicates that multiprocessing should be used during training. After training the model, the code plots the loss and validation loss values over the training process. The loss value represents the difference between the predicted and actual values during training. The validation loss value represents the difference between the predicted and actual values during validation. The plot is displayed in a figure with a title LSTM, training process. This code is used for evaluating the performance of a machine learning model for stock prediction. The variables x_test and y_test are the test data, which consist of features and corresponding target values, respectively. The model variable represents the machine learning model that has been trained on historical stock data. The functions.evaluation function is called to evaluate the model's performance. It takes several arguments: the test data, x_test and y_test, the trained model, a Boolean parameter random indicating whether to use random predictions or not, and the number of predictions to make, n_preds. The function returns three values: pred, y_true, and y_pred. Pred represents the predicted values of the target variable, y_true represents the true values of the target variable from the test data, and y_pred represents the predicted values of the target variable based on the model's predictions. Additionally, the function also plots a graph to visualize the actual and predicted values of the target variable, indicated by the show_graph parameter set to true. This code is setting up a neural network for stock prediction using machine learning. First, the code clears the previous session of the Keras backend. Then, it determines the number of time steps and features in the training data. Next, it creates a sequential model. The model consists of a convolutional layer with 20 filters and a kernel size of 2, using the ReLU activation function. The input shape of this layer is determined by the number of time steps and features. After that, a max pooling layer with a pool size of 2 is added to reduce the dimensionality. Following the pooling layer, a flattened layer is added to transform the output into a 1D vector. Next, a dense layer with 5 units and ReLU activation function is added. Finally, an output layer with a single unit is added. The model is then compiled with the ATOM optimizer, mean squared error, ms, loss function, and ms metric. The code snippet model.summary is used to print a summary of a machine learning model. This summary provides a concise overview of the model's architecture, including the number of trainable parameters and the shape of each layer in the model. It allows us to see the structure and complexity of the model and is often used for debugging and model analysis purposes. The code is fitting a machine learning model to the training data. The model is being trained for 25 epochs, and the training process is not being displayed, verbose equals 0. The validation data is being used to validate the model's performance during training, and multiprocessing is being used for faster training. After the model is trained, the code plots the training and validation loss over the epochs. The loss is a metric that measures the performance of the model. A lower loss indicates better performance. The plot helps visualize how the model's performance improves or converges over the training process. The plot is displayed using the matplotlib library. This code is calling the function evaluation from the functions module with the arguments x_test, y_test, model, random equals false, and _preds equals 50, and show_graph equals true. The function evaluation is likely responsible for evaluating the performance of a machine learning model for stock prediction. It takes the test data x_test and y_test, the model, and some other optional parameters as input. The code then assigns the output of the function to three variables, pred, y_true, and y_pred. These variables probably store the predictions made by the model, pred, the true values of the stock prices, y_true, and the predicted values of the stock prices, y_pred. The use of these variables may depend on the specific implementation and further code. This code is concatenating multiple data frames, specifically stock data frames, into one single data frame called all_stocks. The pd.concat function is used to concatenate the data frames. The parameter stocks represents a list of the stock data frames that are being concatenated. The parameter ignore_index equals true indicates that the resulting data frame should have a new index, ignoring the index values from the original data frames. The given code is part of a stock prediction machine learning model. The first line scales the all_stocks data using the scale function from the functions module. The data is scaled using a scale range of 0 to 1. The next line initializes the number of steps as 21. The third line prepares the training and testing datasets. The split_sequences function from the functions module is used to split the data. It takes in the scaled data, excluding the last row, the shifted return values of the all_stocks data, excluding the last row, the number of steps, a split flag, true, and a ratio of 0.8 as parameters. It returns the training and testing features, x_train, x_test, and labels, y_train, y_test, based on the given ratio. This code sets up a convolutional neural network, CNN, model for stock price prediction. The keras.backend.clear_session function clears any existing models or layers in memory. The variables n_steps and n_features are set to the number of time steps and features in the input data, respectively. The model variable is initialized as a sequential model, which means that the layers will be added in a sequential manner. The model includes a conv1d layer with 500 filters, a kernel size of 10, and the ReLU activation function. This layer processes the input data using convolution, which is useful for capturing patterns in sequential data. A max pooling 1D layer with a pool size of 10 follows the convolutional layer. This layer reduces the dimensionality of the data, which helps to extract the most important features. The flattened layer is added to convert the pooled feature maps into a single continuous vector. The model then includes two dense layers with 500 and 100 neurons respectively, both using the ReLU activation function. These fully connected layers help to learn more complex patterns and relationships in the data. Finally, a dense layer with one neuron in the sigmoid activation function is added as the output layer. This layer predicts the stock price movement as a binary classification problem, increase or decrease. The model is compiled with the Atom Optimizer and the mean squared error, MSE, loss function, which is commonly used for regression problems. This code trains a machine learning model for stock prediction. The model is trained using the x_train and y_train data for 25 epochs. The training process is done in parallel using multiprocessing. After training, the code creates a figure with a plot to visualize the loss and validation loss of the model over the epochs. The loss values represent the difference between the predicted and actual values during training, while the validation loss measures the model's performance on a separate set of data, x_test and y_test. The plot helps to evaluate the model's training progress and identify if overfitting or underfitting occurs. This code is performing evaluation in a stock prediction model using machine learning. The functions.evaluation function is being called with several parameters, the test data, x_test and y_test, the model, a random flag set to true, the number of predictions to generate, n_preds equals 100, and a flag to show a graph. The function will then generate predictions, pred, using the provided test data and model. It will compare the predicted values, y_pred, with the true values, y_true, from the test data. The evaluation process will also include some randomization and it will create a graph to visualize the comparison. This code defines a function called create_model that creates a machine learning model for stock prediction. The function takes in several parameters, including the number of filters, the pool size, and the kernel size. It then converts these parameters to integers. The function then determines the number of time steps and features in the training dataset. It creates a sequential model using the keras library, adding a 1D convolutional layer, a max pooling layer, and flattened layer. It then adds two dense layers with ReLU activation functions, and a final dense layer with a linear activation function. The model is compiled with the ATOM optimizer, mean-squared error loss function, and mean-squared error metric. It is trained on the training dataset for 4 epochs, using the validation dataset for validation. The training is done in parallel using multiprocessing. After training, the model is evaluated on the test dataset, and the evaluation score, mean-squared error, is returned. This code is performing a Bayesian optimization for stock prediction using machine learning. In the beginning, a dictionary called bounds is defined, which specifies the ranges or bounds for the hyperparameters that will be optimized. The hyperparameters include filters, D1, D2, kernel, and pool, and each hyperparameter has its own range of possible values. Next, an instance of the Bayesian optimization class is created and assigned to the variable optimizer. This class takes in several parameters, including the objective function create_model that will be optimized, the specified bounds, a random state for reproducibility, and a verbosity level for logging. The maximize method is called on the optimizer object, with the arguments init_points equals 5 and n_iter equals 5. This method performs the Bayesian optimization, initializing with 5 random points and iterating 5 times to find the optimum hyperparameters. Finally, the optimized result is printed using the print_optimizer.max statement. This code sets the number of steps to 21 and scales the TSLA stock data using a scaling function. It then splits the scaled TSLA data into x_train, y_train, x_test, and y_test using a function called split_sequences. The x_train and y_train data are used for training a machine learning model, while the x_test and y_test data are used for testing the model. The split is done using a ratio of 0.8, meaning 80% of the data is used for training and 20% for testing. The split is based on a predefined number of steps, 21 in this case. The code snippet is calling a function named Bayesian_optimization. It is likely that this function utilizes the technique of Bayesian optimization. Bayesian optimization is a method used in machine learning for optimizing hyperparameters of models. It combines probability and statistics to efficiently search for the best hyperparameters based on an objective function, typically used in tasks like stock prediction. However, without looking into the actual implementation of the Bayesian_optimization function, it is difficult to provide further details on the specific functionality and behavior of the code. This code initializes a neural network model for stock prediction using machine learning. It starts by determining the number of time steps and features in the input data. The Keras backend is cleared to remove any existing models. The model is then created using the sequential class from Keras. It consists of several layers. The first layer is a conv1d layer with 9 filters, a kernel size of 5, and a ReLU activation function. It takes as input a 3D tensor with shape, and steps, and features. Next, a max pooling 1D layer with a pool size of 9 is added to the model. This layer reduces the dimensionality of the data. A flatten layer is then added to flatten the output from the previous layers into a 1D tensor. 2 dense layers are added to the model. The first dense layer has 250 units and a ReLU activation function. The second dense layer has 10 units and a ReLU activation function. Finally, a dense layer with a single unit is added to the model. This is the output layer, as it predicts the stock price. The model is compiled with the ATOM optimizer, mean-squared error, MSE, as the loss function, and MSE as the metric for evaluation. The code is fitting a machine learning model to training data, with 100 epochs, iterations, and it is not displaying any output during the training process. The model is then evaluated using the test data, and the evaluation results are plotted as a graph. The evaluation function used also generates some additional predictions and displays them as a graph. This code is plotting two lines on a graph. The first line represents the returns of a stock, specifically the TSLA stock, for a range of dates from 2000 to 2100. The second line represents a pattern of returns for a smaller range of dates, from 2001 to 2010. The plot is displayed with a title and a y-axis label. This code is a part of a stock prediction machine learning model. The code first converts the stock returns into binary values using a function called binary. It then splits the binary returns into a training set, binary_train, and a testing set, binary_test. The code then defines a variable called step which represents the length of the pattern that the model is trying to find. It also defines check_step which represents the value that the model is trying to predict, which is the value that comes after the pattern. The code initializes an empty list called total_predictions and then starts a loop that iterates 10 times. Within the loop, it checks if the index plus the check_step is greater than or equal to the length of the testing set. If it is, the loop breaks. Inside the loop, the code first initializes an empty list called found_patterns. It then creates a sample of the binary test values, based on the current index and the step length. It also selects the value to be checked after the pattern. The code then iterates through the training set, comparing each sequence of values of length step with the sample sequence. If the accuracy score of the comparison is 1.0, indicating a match, the index of the matching pattern is added to the found_patterns list. Next, the code initializes an empty list called P and a variable called prediction as none. If there are any found patterns, the code iterates through them, extracting the value that comes after the pattern from the training set and adding it to the P list. The code then calculates the prediction as the average of the values in the P list. If the value that comes after the pattern in the test set matches the prediction, a 1 is appended to the total_predictions list. Otherwise, a 0 is appended. Finally, the code calculates the accuracy by summing up the values in the total_predictions list and dividing it by its length. The accuracy is then printed.